Hi there, once again. On this video, you're going to learn about functions. Okay, this is chapter 2 on the Core 3 syllabus. Okay, functions are basically, you've already done functions in Core 1 and Core 2. We're just putting formal terms, the stuff that you already know. Okay, so y is equal to x squared is a function. But if you were to strictly use function notation to describe that, you would have to use it like this. Okay, so f of x, function of x, is equal to this operation. Okay, so this is the sort of correct notation to use for functions. All right, and also a function has to be a 1 to 1 relationship or a many to 1 relationship. Okay, now that sounds a bit confusing at the start, but it's quite straightforward. A 1-to-1 relationship is for every x value there is only one unique y value. Okay, that sort of function is something like this. I'll give you an example of a 1-to-1 function, which is f of x equals x plus 1. All right, so there it's basically y is equal to x plus 1, isn't it? So there is only one unique y value for one unique x value. So I want to sketch that. It looks something like this, wouldn't it? So for every x value, there is only one unique y value. Okay, so that's a 1-to-1 relationship. Okay, so you can define that as a function, right? So that usually it's a linear function. Okay, many to one functions, usually you get that with quadratic functions. Okay, that's when f of x could be equal to x squared. All right, now if I were to sketch that, you all know how to sketch a quadratic by now. So let's say x is equal to 2, then it's y is equal to 4, isn't it, at that point? All right, and then when x is equal to minus 2, oops, let me go somewhere here. Okay, x is equal to minus 2, it's same value, isn't it? Okay, so many values of x equals one value of y. Okay, so that's a many to one function. So you could have 1-to-1 or many to one, and only if you have a relationship like this, it's defined as a function. All right, when the relationship between x and y is either 1-to-1 or many to one, then it's defined as a function. Okay, there is this other scenario where you could have a one-to-many relationship. Now that is not defined as a function. Okay, one to many. Okay, now that sort of situation you get when you try to sketch this graph. Y is equal to square root of x. Okay, now that's a peculiar graph to sketch. Okay, you'll have a one-to-many function, and that one is not a function. This is not a function. Okay, for it to be a function, it has to be either 1-to-1 or many to one. Okay, now let's sketch this graph. Y is equal to square root of x. Before we do that, why don't we work out the coordinates? Okay, so these are my x coordinates and these are my y coordinates. So let me say minus 1, 0, 1, 4. Okay, I'm choosing these values. You'll see why I'm choosing these values and not going up in ones and twos. All right, now square root of 1, so y is equal to the square root of x. So square root of 1 is undefined, isn't it? You can't take a square root of a negative value, so that value is not defined. Okay, square root of 0 is 0, square root of 1 is 1, but is that only just 1? You could also have negative 1. Okay, so we end up with an awkward situation where we are getting two y coordinates for one x coordinate. Okay, now this is a one-to-many situation. Same with the 4, because square root of 4 is 2, square root of 4 is also equal to negative 2. Same with this. Okay, now let's try and sketch this. So you won't have any negative x values defined. Okay, so therefore I have to start from 0. So at 1, it's at 1. Now let me put it somewhere here. And at 4, it's at 2. And at 9, it's at 3. okay, but I've only sketched one part of the thing. Okay, I've got to sketch the negative values as well. So at 1 it's also -1, at 1 it's also -2, at 1 it's also -3. So the actual function, well, I can't call it a function because it's a one-to-many relationship. So the graph looks like this. Now this sort of relationship is not a function, okay, because you have a one-to-many relationship, so therefore it's not a function. Okay, remember that you got to have either a one-to-one or many-to-one situation, all right, for it to be defined a function. Good. Now we'll look at something else to do with functions. Okay, you talk about the function's domain and the range. Okay, now you know these intuitively from core 1 and core 2 from the graphs you sketch for the functions. Okay, but we're just formalizing everything that you've learned so far. All right, so the domain is basically all the x values that the function could take. The range is basically all the y values that the function could have. Okay, let's take an example. Okay, simple function, simple linear function, y is equal to x plus 1. Okay, now if I want this function to take any value of x, okay, how far could you go with x? Could you stop at 100? Do you want to stop at -100? Or do you want to go as far as you can? That's basically infinity, isn't it? Infinity to -infinity. So if I want this function to take any values of x between infinity and -infinity, I say the domain, so I say x includes, I got to put this weird e sort of sign, okay, includes, I've got to say, if it's all numbers between infinity and -infinity, that means it's all real numbers. Okay, now you would be wondering, why can't I just say all numbers? Okay, because in maths there is this distinction between real numbers and imaginary numbers. If you do some higher maths, you'll learn about imaginary numbers. Okay, but this can take only real numbers. So that's basically all the numbers that you know. You only know the real numbers. Okay, imaginary numbers you'll learn later. So that's why you say if you can take any x value between infinity and -infinity, you say x includes all real numbers. Okay, you know how the function looks like. It looks something like this. So if you want to, that's that one. If you want to stretch it, you can stretch it at both ends. Okay, so that's the domain. Okay, the domain is all real numbers. What about the range? Range tells you all the y values it could take. Okay, so in the y direction as well, the function could have anything from infinity to -infinity. So therefore the range is also includes also all real numbers. I got to write an r and shade it in a bit. Okay, there's another way of writing the range. Okay, it's a bit more fancy. You say f of x. Okay, when you talk about f of x, you're talking about the y coordinates includes all the real numbers. Okay, because now we're trying to stop writing it in this form, functions. We're going to start writing it like this: f of x is equal to x plus 1. So basically when you talk about f of x, you're talking about the y result. Okay, so instead of the y, we're going to put this. So we're going to persist with this. Now we're not going to this is not wrong, still right, but it's better to persist with this. Even in an exam, if you write it like this, y includes all real numbers, you still get it right, but it's better to persist with this because a question usually gets asked in this form. Okay, right. Now let's say the same function y is equal to, oh, I'm going to stop saying that. The function is equal to x plus 1. All right, now I'm going to put a restriction on the domain. I'm just going to say x is greater than or equal to all greater than or equal to 0, and its x also includes all real numbers. Okay, so how would I sketch this? Now if I say x is greater than or equal to 0, I got to start the function here, okay, and go up like this. Okay, the actual function would have this red bit as well. Okay, but I can't include that red bit because my function is now restricted by this domain. Okay, where I got to start from x is equal to 0 and go up from there. Okay, so what y values would I have from the place where I started drawing the function? Okay, so my y values, or my fx values basically, so that's the range. So this is the domain and this is the range. So at x is equal to 0, y is equal to 1, isn't it? That's the intercept basically. Okay, so my y values start off from 1 and it goes on till infinity. So f of x is greater than or equal to, f of x is greater than or equal to 1, and also f of x includes all real numbers. Okay, now this statement doesn't negate this statement here. You're saying all the y values includes all real numbers and the y values have to be greater than 1. Okay, it's not one or the other, it's both. Both these statements have to be true. Same with the domain. The domain, x has to be greater than 0 and x includes all real numbers. Okay, so that's how it works. Good. All right, so let's look at another function. Let's look at a quadratic function. Let's look at y is equal to x squared plus 2. All right, now for this one, okay, I'm not going to put any restrictions on the domain. So x includes all real numbers. Okay, so that means x could have any value from infinity to minus infinity. But how would this function look like? Okay, it's the basic quadratic graph shifted 2 spaces up, isn't it? Right, so the minimum points there is 0, 2. Okay, so for the domain it includes all real numbers. What about the y coordinates, or f of x? That includes all real numbers, and if you notice, this function would never go below this point where y is equal to 2. So this function does not have any values below this. So f of x is greater and equal to 2. Okay, so for this function, both these restrictions are true. Okay, for the range, that it does not go below 2, so therefore it could have any value above 2 up to infinity. And I also put this saying that it includes all real numbers, but all those real numbers have to be greater than 2. Okay, good. Okay, now let's look at another function. Okay, so let's look at this function, the reciprocal function. All right, a reciprocal function would have an equation of this sort. Okay, right, now you got to think back to your core 1 syllabus now. Okay, so I'm just going to slow it down a bit and build it up from the basic reciprocal function. So the basic reciprocal function is y is equal to 1 over x. How would that look like? Okay, it would look like something like this. So then I've got to do a transformation on that. I've got to do, if this was f of x, if I did f of x plus 2, that means it goes up by 2, doesn't it? So the equation changes to this. And if I were to sketch that, the function would look something like this. Okay, same function shifted up 2 spaces. Okay, right, now for this one, when I specify the domain, I'm going to say it includes all real numbers, but there is an asymptote, isn't it? There are 2 asymptotes when you draw reciprocal functions. One asymptote is here when y is equal to 2. The other one is here. Okay, I can't show that asymptote because it's on the axis when x is equal to 0. The function is not defined for that value, x is equal to 0. So I can't include that as part of my domain. Okay, because when x is equal to 0, y is infinity, but infinity does not have a value. Okay, so therefore it's undefined. Okay, the function is this, isn't it? Y is equal to 2 plus 1 over, instead of x I put a 0. 1 over 0 is infinity, but infinity is not defined in maths, so this is not defined. So therefore when x is equal to 0, the function is not defined. Same thing happens when y is equal to 2. Okay, when y is equal to 2, the function is not defined. All right, so therefore that takes effect in the range. So f of x, the range could have any real numbers, but the range could not have a value of 2. All right, so wherever the asymptotes are, those values are not defined if they appear on the range or the domain. Okay, so that's how it works out for the reciprocal functions. All right, good. Okay, now we'll move on to something else. Okay, we'll move on to composite functions. Composite functions. All right, so composite functions, basically, now let me define two functions. Okay, now one in terms of f. Okay, I'll say that is x squared plus 2. Another one in terms of another letter. Okay, it's still a function, but I'm just going to use a different letter. All right, so gx. All right, x plus 1. Okay, let me make this slightly simpler. I'm going to make that x plus 2, not x squared plus 2. All right, now a composite function may be looking something like this. It may look something like this. All right, so what you have to do here is you got to put this function for g inside the f. Okay, so wherever you see x for this function f, that is basically an x plus 1. Okay, so if it's written like this, you got to put this x plus 1 into the x. So x plus 1 is substituted for x. So therefore fgx is basically x plus 3. Okay, now we look at something harder. So if I make fx x squared plus 2, and then gx, I'll keep it the same, x plus 1. Now in this instance, if I want fgx, I've got to put x plus 1 instead of the x. Now that's the new function. All right, so you can leave it like that, or you can expand it and then simplify it. Okay, so you can that's a 2. All right, so you can leave it like this if you want to. All right, sorry, that is in fact a 3. That's a 3 there. Okay, right, so that's the composite function. Basically you put one function into another. Okay, it's pretty straightforward. All right, now next we'll look at inverse function. Okay, now this is slightly complicated. All right, inverse functions. Okay, now graphically what that does is any function that you have, all right, it just reflects it on the y is equal to x line. That's when you do an inverse function, that's what you get, that's what you see graphically. All right, okay, so you have your y is equal to x line. All right, so when you do an inverse function, it just reflects something on the y is equal to x line. All right, so let's look at the yellow line. The yellow line could have a function of this sort, f of x 2x plus 3. all right, 2x plus 3. So if I say y is equal to 2x plus 3, all right, to figure out the inverse function, even if it's written down in terms of f of x, you turn that f of x back into y. All right, what you've got to do is you got to swap the letters. All right, so I'm going to change that y into x and x into y. Swap the letters. All right, y into x and x into y. And then what I do, I try and make y the subject. So that's x minus 3 is equal to 2y, and y is equal to, I got to divide the whole thing by 2. So let me divide each term by 2. So y is equal to x by 2 minus 2 by 3, 3 by 2. All right, now this is in fact what is shown with this green line. Okay, okay, this equation is shown by the green line. Okay, you can see that the green line has a smaller gradient, all right, and its intercept is actually below the origin, isn't it? Because the intercept is minus 3 by 2, whereas the intercept for the yellow one was 3. Okay, but if I sketch these two graphs, it will be a reflection on the y is equal to x line. All right, so that's how you work out an inverse function. You just write the function in terms of y and x, and then swap the letters and try and make y the subject, and you'll get its inverse function. All right, good. In questions where you have to do an inverse function, they tend to ask what happens to the domain and the range. Okay, now for this function I did not define a domain. All right, now let me just restrict the domain here. All right, for this function, so fx 2x plus 3, let me just restrict the domain saying x has to be greater than or equal to 0, and x could include all real numbers as well. Okay, but x has to be greater than 0. Okay, so if you were to sketch that, you'd only get this part only. All right, do not sketch the other bit because the domain is restricted, because x is greater than or equal to 0. Right, now you know what the inverse function is. The inverse function is basically x y is equal to x by 2 minus 3 by 2. So I'm still going to use the fx notation to show the inverse function. Now if you want to show the inverse function using fx notation, you've got to put a minus 1 there. All right, it's not a dash. All right, that means you've differentiated it. Okay, it's not the differential, it's the inverse, so you've got to put a minus 1, and the inverse function is x by 2 minus 3 by 2. All right, now for the domain for the original function was x greater than 0. All right, what was the range then? So f of x has to be greater than 1, isn't it? All right, and it's also inclusive of all real numbers, but x has to be greater than 1. Okay, so that point there is 0, 1. That's the range for this domain. All right, what happens when you do an inverse function is that, okay, let me write this out clearly. Okay, so this is the normal function, and that's the inverse function. The domain we saw for the inverse normal function was x is greater than 0. The range we saw for the normal function was fx is greater than or equal to 1. So for the inverse function, the range of the normal function becomes its domain, so x is greater than or equal to 1, and the domain of the normal function becomes the range of the inverse function, so f of x is greater than or equal to 0. Now let's see what happens when we sketch this function within these limits. Okay, f of x is equal to x by 2 minus 3 by 2. X has to be greater than 1. Okay, so the least possible x value it could have is x is equal to 1. X is equal to or greater than 1. So if I substitute a 1 in there, that's a minus 1. So when x is equal to 1, the y coordinate is minus 1. So that's where I start sketching this function. So when 1 and minus 1, that could be somewhere here. All right, and then the function looks something like this. Oops, I can't draw it curved. It's a straight line. It looks something like this. Okay, right, so for that function which has a restriction on its domain, the inverse function would look something like this, and the y coordinate or the